Researchers at a major medical institution wanted to understand exactly what the liver was doing during a 24-hour fast. Not approximately, not in animal models, in human subjects, with metabolic tracers that could follow specific molecules through specific biochemical pathways in real time. What they found changed the picture of liver metabolism during fasting in two specific ways. First, beta-oxidation in the liver, the process by which fatty acids are broken down for energy, more than doubled at the 24-hour mark compared to subjects who had only fasted overnight. The liver was not gently shifting into fat metabolism. It was running fat processing at more than twice the rate. Second, when they ran the same protocol on subjects with non-alcoholic fatty liver, the liver's response was different in a way the researchers did not fully anticipate. Beta-oxidation increased, but ketogenesis, the process by which the liver converts those broken down fats into ketone bodies for export to the rest of the body, was impaired. Instead of converting fat into exportable ketones, the fatty liver was routing the process material through a different biochemical pathway, the TCA cycle, in a way that consumed the products internally rather than sending them out to fuel the brain and other organs. The fasting liver was revealing exactly what metabolic state it was in, and the two responses, healthy liver versus fatty liver, were measurably, quantifiably different. This is the organ that changes first when you stop eating, and how it changes, and when, and in what sequence, tells you more about your metabolic health than almost any other measurement. Think of the liver as the most complex processing plant in the body. Under normal fed conditions, this plant is receiving constant incoming shipments, glucose from digestion, fatty acids from the diet, amino acids from protein breakdown, and converting them into dozens of different products the body needs. It packages glucose for distribution. It synthesizes proteins. It filters toxins. It manages cholesterol. The plant never closes, never stops processing, and handles more than 500 distinct biochemical reactions simultaneously. When fasting begins, the incoming shipments stop, and the plant does not shut down. It switches what it produces in a precise sequence, driven by a cascade of hormonal signals that begin the moment blood glucose starts to fall. Here is what happens in each phase. Phase 1, hours 0 to 8. Glycogenolysis, releasing the stored fuel. The liver is the body's primary glycogen depot, holding approximately 100 to 120 grams of stored glycogen at any given time. The moment blood glucose begins to fall after a meal is digested, the pancreas detects the drop and increases glucagon secretion. Glucagon reaches the liver and signals it to begin glycogenolysis, the breakdown of stored glycogen into glucose molecules for release into the bloodstream. During this phase, the liver is acting as a battery, discharging stored energy to maintain blood glucose stability. The processing plant is not yet running on a different fuel. It is running down its emergency reserve. What the body feels during this phase is largely nothing. Blood glucose stays stable because the liver is compensating. The shift is biochemical, not experiential. Most people eating 3 meals per day never push past this phase because the next meal arrives before the reserve is significantly depleted. Phase 2, hours 8 to 18. Gluconeogenesis, manufacturing glucose from scratch. As glycogen reserves begin depleting, the liver transitions to gluconeogenesis, the synthesis of new glucose from non-carbohydrate sources. The primary substrates are lactate from muscle metabolism, glycerol released from fat cell breakdown, and amino acids from protein turnover. The plant has run out of its prefabricated stockpile and is now manufacturing the product from raw materials. Gluconeogenesis is energetically expensive. The liver is consuming more energy to produce each unit of glucose than it was spending during glycogenolysis, and the rate of production cannot fully replace the rate that glycogenolysis could sustain. Blood glucose stability begins to depend on the interplay between this manufacturing rate and the declining demand from tissues that are beginning to accept alternative fuel sources. Insulin is falling continuously during this phase. AMPK is rising. The conditions for the next transition are building. Phase 3, hours 18 to 24. Ketogenesis, the metabolic switch activates. This is the most consequential phase for the liver specifically, and for the whole body's fuel supply. As glycogen depletion advances and insulin falls below a critical threshold, the liver begins ketogenesis, the conversion of fatty acids into ketone bodies, specifically beta-hydroxybutyrate, acetoacetate, and acetone. These 3 molecules are the liver's export product for extended fasting. They can cross the blood-brain barrier, fuel the heart, and supply most of the body's tissues with energy without requiring insulin for cellular uptake. The metabolic switch from glucose-based to fat-based metabolism is not an instantaneous event. As the superpower research describes it, it is more like a dimmer switch, gradually increasing fat oxidation and ketone production as glucose availability declines. Trace ketones may appear before full glycogen depletion. Meaningful ketone levels, where ketones become a primary fuel source, typically appear after 18 to 24 hours in most people eating a standard diet. The plant has changed its primary product line. It is no longer primarily manufacturing glucose. It is manufacturing ketones, the fuel that the rest of the body can use when glucose becomes scarce. This is also where the difference between a healthy liver and a fatty liver first becomes detectable by external measurement. A healthy liver at this phase, beta-oxidation accelerating, ketogenesis activating, blood ketone levels rising measurably. A liver with significant fat accumulation, beta-oxidation may increase but ketogenesis is impaired, with the processed fatty acids being diverted into TCA cycle metabolism instead of ketone export. The ketone level at hour 24 is a readout of how efficiently this transition has occurred. Phase 4, hours 24 and beyond, beta-oxidation more than doubles. The JCI study published in PMC in 2023, measuring hepatic fat oxidation with metabolic tracers in fasted human subjects, found that 24 hours of fasting induced beta-oxidation in the liver at more than twice the rate of overnight fasted subjects. More than 2 times, not a marginal increase, a categorical shift in how much fat the liver is processing per unit of time. Beta-oxidation is the sequential breakdown of fatty acid chains, each cycle shortening the chain by 2 carbon units and releasing acetyl-CoA, which then feeds into either ketogenesis or the TCA cycle. More than doubled beta-oxidation means the liver has fundamentally changed its operating mode. It is now primarily a fat processing facility. And within this phase, the distinction the researchers found in fatty liver subjects becomes most significant. In subjects with non-alcoholic fatty liver, the same increase in beta-oxidation occurred, but the downstream routing differed. Instead of the acetyl-CoA being converted to ketones and exported, it was entering the TCA cycle at a higher rate. The fatty liver was processing fat but not efficiently converting the products into the exportable fuel that the brain and other organs need. The plant was running its machinery but sending the output to internal storage rather than the distribution dock. Phase 5, extended fasting, hepatic autophagy. In the liver specifically, autophagy has a function beyond general cellular cleanup. The liver accumulates damaged proteins, dysfunctional mitochondria, and excess lipid droplets in the course of its continuous high-intensity processing work. These accumulate faster in the liver than in most other tissues because of the metabolic load it carries. During extended fasting, beyond 24 hours, hepatic autophagy runs at the depth required to process this backlog. Research on the role of autophagy in the liver has confirmed that it is essential for maintaining hepatic metabolic function. Impaired liver autophagy is directly linked to increased hepatic fat accumulation, reduced mitochondrial quality, and progression toward non-alcoholic fatty liver disease. The liver during extended fasting is therefore simultaneously producing ketones for the rest of the body and cleaning its own internal machinery. The processing plant is running its product lines and doing its maintenance during the same window, a combination that the continuous fed state does not allow because the production demand is always too high for the maintenance crew to run effectively. Before the protocol, fasting beyond 24 hours carries specific risks for people with existing liver conditions, diabetes, conditions affecting glucose regulation, or who take medications affecting metabolism. Anyone with a known or suspected liver condition should speak with a hepatologist before attempting extended fasting. The mechanisms described here represent general hepatic biology in healthy adults and do not constitute a treatment protocol for any liver condition. Electrolyte monitoring during extended fasting is critical, particularly as glycogen depletion releases stored water and electrolytes that need to be replaced. The liver's response to fasting is not passive. It is the most active metabolic adaptation in the body during food absence. Its glycogen determines how long the first phase lasts. Its ketogenesis capacity determines how efficiently the rest of the body transitions to fat fuel. Its autophagy function during extended fasting determines whether the organ itself remains clean enough to continue doing its 500 jobs. And the ketone level at hour 24 is the simplest external measurement of how all 3 of those systems are working. If this changed how you think about what your liver is doing every time you fast, subscribe and leave a like. Tell me in the comments. Did you know the liver's response to fasting was this specific and this sequential? Or did you think fasting just meant the body running low on energy?